Welcome all to the video that brings to you a few interesting facts on eigenvalues and eigenvectors. Consider a 2 by 2 matrix 5, 4, 1, 2. Here you can notice that the column sum, that is, the sum of elements across a column, is remaining the same. 5 plus 1 equal to 6, 4 plus 2 is also equal to 6. However, the row sum is not same. 5 plus 4 is equal to 9 and 1 plus 2 equal to 3. If either of the row sum or the column sum remains the same, then that particular sum value is possibly one of the eigenvalues. Another important fact is that the determinant of the matrix always equals the product of the eigenvalues. For example, the determinant of this matrix is given by 5 into 2 minus 1 into 4, which is equal to 6. Also, the product of eigenvalues is given by 6 into 1, which is also again 6. The sum of eigenvalues always equal to the sum of diagonal elements of the given matrix. Here, the sum of eigenvalues is 6 plus 1, 7, and sum of diagonal elements of the given matrix is 5 plus 2, which is equal to 7. A quick note on eigenvectors. An eigenvector is a column matrix which is the non-zero solution matrix for the equation a minus lambda I into x equal to 0. Hence, an eigenvector can never be a zero vector. Now, if you consider a 3 by 3 matrix and you're interested in finding out the eigenvalues and eigenvectors of the matrix, the first step will be to evaluate the characteristic equation, which is given by determinant of a minus lambda I equal to 0. Whenever you have a 3 by 3 matrix, the characteristic equation will be a cubic equation in variable lambda, and you can easily find out the eigenvalues by looking at this cubic equation. The trick involved is that coefficient of lambda square will give you negative of sum of eigenvalues and the constant term will give you negative of product of eigenvalues. So, looking at the constant term and taking the negative of it, you get the product of eigenvalues. 45 is the product of eigenvalue here, and the negative of coefficient of lambda square, which is equal to negative 1 here, will give you the sum of eigenvalues. So 45 has to be factored such that the sum of factors will give you negative 1. So 45 when factored as 9 into 5 will not give you the sum as negative 1. 45 when factored as 15 into 3 will also not give you the sum negative 1. So you will look for the possibility of factoring 45 as minus 3 into minus 3 into 5, which will yield us the sum minus 3 plus 5, which is equal to minus 1. Hence, these factors will give you the eigenvalues. Having found the eigenvalues, we can go to the evaluation of eigenvector. Eigenvector is found using the formula a minus lambda I into x1 equal to 0. Lambda is replaced by minus 3. You get a resultant matrix, and the simplified form looks like this. This matrix involves all the 3 rows which are linearly dependent. Why are the rows linearly dependent? Because every row can be considered as a scalar multiple of the other. Every row, when multiplied by a scalar quantity, gives the other row. So this is a case of redundancy. Just like in case of vector multiplied by a scalar, you get an elongated vector or a vector in short length. We are not obtaining any geometrically different vector by a scalar multiplication of vector. Similar way, here considering the 3 rows is in net effect representing only 1 row. So we are interested in taking only one linearly independent row, and any of the 3 rows can be selected as the linearly independent row. If we select the first row and multiply it by the column vector, you get the resultant linear equation x1 plus 2x2 minus 3x3 equal to 0. From there, you get the relationship of x1 in terms of x3 and x2. So you can write the eigenvector x1, x2, x3 as 3x3 minus 2x2, x2 and x3. This can be splitted as sum of 2 vectors, sum of 2 column matrices. Here, if you replace x3 and x2 by scalar values k1 and k2, you get this vector. So what is the representation of eigenvector for lambda equal to minus 3? It is a scalar multiplied to these vectors and addition of these 2 column matrices. Going for the evaluation of eigenvector for lambda equal to 5, you go for the equation a minus 5i into x2 is equal to 0. Here, the usual sequence of steps will give you a simplified matrix of this form. Here there are no linearly dependent rows, so the usual shortcut method will help you to find out the values of x1, x2 and x3. Whenever you have a linearly dependent row here, it is possible that you get zero solutions for x1, x2, x3, and a zero vector is not possible as an answer for eigenvector. So you have to adopt techniques of finding x1, x2, x3 in this manner. If you consider another example, a 3 by 3 matrix, here you can see that this matrix is an upper triangular matrix. Whenever you have an upper triangular matrix or a lower triangular matrix or a diagonal matrix, the eigenvalues are nothing different from the diagonal elements. Having found the eigenvalues, you go for the evaluation of eigenvector. When you apply the formula a minus lambda I into x equal to 0, for the eigenvector lambda equal to 2, you see that the simplified form of the matrix looks like this, and here also you can see that there are linearly dependent rows. This row is linearly dependent to this row because the last row multiplied by a scalar 2 will give you the second row. So these two rows are linearly dependent rows. So we are interested in only linearly independent rows. So either you can select the first row or the second row, or first row and the third row. When you multiply it, the first row into the first column gives you the first equation. Similar way you can find out the second equation and the third equation by matrix multiplication. From these two equations, you get x3 is equal to 0. Whether you consider equation 2 or equation 3, you obtain x3 equal to 0. When x3 equals to 0 is substituted in the first equation, you get the relationship between x1 and x2. Looking at this ratio, you can easily write the eigenvector corresponding to the eigenvalue lambda equal to 2. When you evaluate the eigenvector for lambda equal to 3, you follow the same steps. A minus lambda I into x2 is equal to 0. Here you can see that there are no linearly dependent rows. So the usual shortcut method will be successful and you are getting a non-zero vector as the eigenvector. When you try to find out the eigenvector corresponding to lambda equal to 5, after simplification of the steps, a minus lambda I into x3 is equal to 0, you get a 0 row here, which will yield as a 0 solution, and a 0 solution is not possible when you try to find out eigenvector. So you consider only the linearly independent rows, which are the first and second one. Looking at the first and second equations after matrix multiplication, you get the relationship between x2 and x3. Also the relationship between x1 and 3x3. Substituting the values for x1, x2, x3, taking out the common factor x3, you get the vector 3, 2, 1, and any scalar multiple of 3, 2, 1 will also be an answer for eigenvector corresponding to the eigenvalue lambda equal to 5. Thank you all.